Left-hand side just has the physical interpretation of the kinetic energy of the electron. Okay, so maybe when these electrons are traveling around, they will have kinetic energy described by this equation in this wave function, this side of r. Sorry, this is side of r. And then how do I describe the fact that these electrons are trapped like microwave, trapped in a microwave cavity? Well, you can add some kind of a potential wall. So what he did then was that he said that this actually is equal to kinetic energy. If I add a potential energy term to this, and this could be describing the potential energy of the electron, this is the kinetic energy of the electron, and if I demand that this always be a constant, then maybe I have it made. This is actually called a Schrödinger equation that was concocted by Schrödinger in his very early days. VR can be the potential that electron sees, and VR is be a Coulomb potential. So if you were to look at the Coulomb potential, electron sees a potential that is like that. This is like what we call a potential wall. Potential wall can be used to trap wave. Just like if I were to draw the analogy of this that you have learned in 350, it's like a dielectric waveguide. If you have a dielectric waveguide in one dimension, you learn that Maxwell's equations can be written in this manner. Maybe something like plus k squared z by z. Maybe I can write this as omega squared mu epsilon z psi z equal to 0. Okay. So if I were to have an epsilon z, it looks something like this. Maybe one out here, you can use the relative permittivity, and then maybe 2 in here. I know that it can trap a mode inside this dielectric waveguide. Okay, I can trap a mode inside this dielectric waveguide, and then and if you want to put in the other terms of the and this can be the equation for a dielectric slab waveguide, for instance. You look for kz's, kx maybe, kx is into the blackboard, okay? Kx, where you will look for this thing that will give you a trap mode, okay? But then because of the minus sign in Schrödinger equation, the wall looks the opposite direction. Okay, in the dielectric waveguide, you have a high index material to trap a mode, but for Schrödinger equation, you have to have a low potential wall to trap a mode. Okay, because of the similar kind of physics here, you can use this because of this negative sign. In order to trap a mode, you need a negative potential wall. Okay, and then E is like the energy of the total system. E is equal to kinetic energy plus potential energy. Is the total energy of the system is always has to be constant. And Schrödinger came up with this idea, and then using this idea, he was able to predict a lot of spectroscopic observations you can see in chemistry. And hence, this equation is named after him. Okay. And then, of course, There are other things you can do to Schrodinger equation. You can see that maybe there are dependent phase functions of this sort that, in addition to these wave functions that you have over there, perhaps you can introduce a kind of time dependence. Sorry that I use e to the minus I omega t, because all electrical engineers love e to the j omega t. Okay, but most physics and optics books use e to the minus I omega t. Okay, you just have to learn how to switch between the two. Minus I is j, minus j is I. Okay. So then, if you were to take the time variation of this function, then you get minus I omega by r e to the minus I omega t. And then if you were to further multiply this by IH, partial t psi, you get h bar omega sine r e to the minus I omega t. H bar is something like energy, as we have learned from photons, photoelectric effect, as well as Planck's radiation law. So perhaps we can connect this E to h bar omega, and because of writing that E as h bar omega, then the right hand side can become just this thing, and then you have this Schrodinger equation, which is known as the time-dependent Schrodinger equation. So you can put in time dependence in here, and conjecture that there is a time-dependent Schrodinger equation that looks something like that. Okay. You want to say something? Yes, about.
We can just start with step 2.
Yeah, you can. So the thing is that this kind of equation is very much reminiscent of classical mechanics, because this can be thought of as a Hamiltonian operator operating on this is equal to that. So in a sense, people drew a lot of inspirations from classical mechanics. This is something called the Hamiltonian. Hamiltonian was well known in classical mechanics for a long time before it appears in quantum mechanics. So I thought that it would be worthwhile for us to go through some knowledge of classical mechanics, and I'd like Ayin to give you a lecture on classical mechanics, so that you can see later on how classical mechanics connects to quantum mechanics.
Do we give them a 5-minute break?
Yeah, I think we don't need to, right? Okay. You need a break? I guess you don't need a break.
No, you don't need a break. Okay, so I'm going to review for you guys the essence of classical mechanics. And of course, you've had some classical mechanics. No doubt you've already known the Newtonian formulation of classical mechanics. But today we're going to teach you 2 equivalent formulations. Okay, so as you have seen, the wave function says that in quantum mechanics, we have the wave function in connection with a probabilistic interpretation. And that says that the world is not deterministic. That is not the view in classical mechanics. The basic view in classical mechanics is that if I have some system and at some initial time I specify all of the coordinates and velocities, then the state of the system is completely determined, and its subsequent motion can be calculated through what are called the equations of motion. So So the task of mechanics is to write down the equations of motion. And these equations of motion, as you've probably seen in Newtonian mechanics, they are relations between acceleration, velocities, and coordinates. So they're in general second-order differential equations in time. So we write down the equation of motion, and then subsequently we will integrate the equations of motion to solve for the time evolution of the system. Okay, so that is the task of classical mechanics. And there are several ways of formulating the equations of motion, and the systematic ways fall into two branches. And the first one and the oldest one, this is called Newtonian formulation. And in this branch, everything is based on two vectors, which we call the force and the momentum. Okay, two vectors. And the composition of the equations of motion are, of course, as you know, governed by Newton's laws. Okay, so this is the first branch. And because it's based on two vectors, we call this the vector branch. Okay. And then there's also a branch of classical mechanics known as the analytical branch. And these are later developed by Lagrange and Hamilton. And respectively, they are the Lagrangian mechanics and the Hamiltonian formulations. And in these two, everything is based on two scalar functions, which are the total kinetic energy of the system and the total potential energy of the system. And we use T to denote the total kinetic energy. So I'm going to go through Newtonian mechanics first, but this should be reviewed for everyone. Okay. So in Newtonian mechanics, we start with something you all know, that the time evolution of the momentum is governed by the force. Okay. And this is, of course, Newton's second law. Okay. And then in turn, the momentum in turn governs the time evolution of the coordinates. And we will use Q to denote the coordinate, not X. And this is just customary. Okay, and this is Newton's first law. Okay, and of course the third law concerns the characters of the force. And now there are two kinds of forces that we should distinguish. Okay, there are forces that you probably remember this from your mechanics course. There are forces that are conservative, and they derive from a potential. We may write them as the gradient of some potential function. And there are forces that are non-conservative. Okay? Non-conservative forces will introduce dissipation into the system, and energy is going to dissipate into non-mechanical forms. And in Newtonian mechanics, there is little distinction between these forces. Because in Newtonian mechanics, you start with the concept of the force. So there's really no restriction on the nature of the force. Newtonian mechanics is equally well in dealing with these two types of forces. Now suppose that for every coordinate and every particle in the system, we have formulated the net force on them. Okay, then we can write down the equation of motion, and then we can subsequently integrate the equation of motion. And Newtonian mechanics is very well suited for numerical techniques. Okay. But I think I'm not going to go through that because we're running out of time.
Since we don't use the dot notation in electrical engineering very often.
Oh, okay.
Explain
So sorry. The dot means time derivative. Okay. Now, and it means ddt. Okay, the total time derivative. This is to be distinguished with the partial time derivative, which takes care of only the explicit time dependence. Okay. So next, let's move on to the Lagrangian formulation. And before that, I want to point out one point is that in the Newtonian formulation, you start with these equations of motion. You see that everything is in terms of cause and effect. Okay? The force causes an acceleration. So the whole picture is causal, and you can think about the system as evolving in a time-stepping fashion. Okay, that is not the case in the Lagrangian formulation. In the Lagrangian formulation, we're going to start with something called the Lagrangian of a system. And it is defined as the kinetic energy the difference between the kinetic energy and the potential energy. Okay, so I've written the dependence of each energy term as well.
With the first term, do you also dependent on time?
The kinetic energy is not explicitly dependent on time. That is always the case. But we allow in general for a time-dependent potential. Okay. And then the Lagrangian is dependent on the coordinate and the velocities of the system, which is just a restatement of what we started with, which is the deterministic character of classical mechanics. Once you have specified the coordinate and the velocities, the system is known. So there should be no dependence on higher order derivative. Okay, so this should make sense to you. Now, next we are going to define the time integral of the Lagrangian. And this quantity is known as the action. So say the system evolved from time t1 to t2. Then the time integral of the Lagrangian is, of course, written as this. Okay. And in the Lagrangian mechanics, the composition of the equations of motion is guided by a principle known as the principle of least action. Which states that the system will evolve in such a way so as to minimize the action integral. Okay. So how do we minimize a definite integral? You can think about the machinery of this computing the action as you take the input as some function of the time, some function of time, and also its time derivative. And then you compute this Lagrangian, you take the time integral and you output a real number. So this type of structure is called a functional. Okay. And in the calculus, there is a specific branch of calculus known as the calculus of variations. That is dedicated to finding the extreme of minimizing functionals. Okay. So we can imagine how to do this pictorially by drawing what's called a space-time diagram. Okay, so let's specialize to a one-dimensional situation where I have one axis denoting the time, and I have one axis denoting the coordinate. Okay, and the integral from t1 to t2 sets the boundary conditions. So let's say that the system starts from t1 to t2, and we know the coordinate. So we're doing fixed endpoint physics. Okay, and any line that connects, any curve that connects these two, it defines a path that the system evolves through. Okay. And now we can just start with an arbitrary guess of a path. And then we can add infinitesimal corrections to the path in the form of some perturbing function of time. So that brings us to a new path, but we will, since we are fixing endpoints, we will require that the corrections we add vanishes at the endpoints. Okay. Now we start from the original path and we go to the new path, and then we compute the action in two cases, and we find when the action is stationary under infinitesimal corrections to our path, and that you will find the correct path for the system to evolve. Okay, and to do that, okay, what we will do is for the new path. So we take q, and it goes after the variation. It goes to q plus epsilon eta of t. So this eta is some arbitrary function with vanishing endpoints. Okay. And then this epsilon is just an infinitesimally small quantity. Okay. And then of course the time derivative of q goes into this. Okay. And then the new Lagrangian. Okay, let's just formally it's just I plug in the updated arguments. And then I take the difference with the old Lagrangian. Okay. I do this integral over time on this interval that I have defined. And this computes the variation in S due to variation in Q. Okay. And now the question is, how do we actually evaluate this difference? We can think about it as doing a Taylor expansion. Okay. And in doing that Taylor expansion, we're going to fix time at every point. And because we fix time, the velocities and the coordinate is decoupled. So they're completely independent of each other at each time instant. Globally, they are dependent. And we have already taken care of that dependence by doing the variation of coordinates. Okay? But when we do the Taylor expansion, we can see them as independent. Okay, so to doing the Taylor expansion, which you guys must remember how to do. Okay, we're going to have the zeros order term canceling with the original Lagrangian. So let's keep terms of first order in epsilon. So that's going to be okay. This is just doing a Taylor expansion. Okay, and then the next thing we like to do is to bring out a common factor. We would like to bring out the common variation outside. But now there is a time derivative acting on the time variation. So what we're going to do is we're going to do an integration by parts on this term. Bring the time derivative off of the eta onto here. Okay. So doing the integration by parts, we're going to get an integrated L piece, which corresponds to okay. And this is evaluated at the two endpoints. But because we have insisted on fixed endpoint variations, this term simply just vanishes. Okay. And then what we're left with is, of course, the first term carries over. Now let me group some terms together. Okay. So I've taken out the eta as a common factor. And then this is the first term. And then the second term after integration by parts will acquire a minus sign. Okay, and remember we need to do the put the time derivative on it right now. Okay. Okay, so this is what we're left with, and this is equal to the variation in S. Okay, and now we apply the principle of least action, which says that the variation will vanish for the path that the system actually traverses. So we set this to 0, and because the arbitrariness with which we have chosen the small variation function, we can just say, we can conclude that this term must go to 0. Okay. So now we have derived the equation of motion in the Lagrangian formulation. And this is called the Euler-Lagrange equation. Okay. This is the Euler-Lagrange equation. And it is very simple to show that the Euler-Lagrange equation is actually equivalent to its Newtonian counterpart. But it's simple to show through a specific example, but the general problem we're not going to treat them here because that's quite involved. Okay, so let's consider a simple Lagrangian describing a collection of particles interacting through some potential. Okay, so that is going to look like, we know how to write down each of the kinetic energy of each particle. This is the sum of the kinetic energy of each particle, minus the interaction potential. And the potential is in general going to depend on every particle's coordinate. Okay, and let's say that it's not time dependent for now. So we have a closed system. And now we just, for each coordinate, we're going to apply the Euler-Lagrange equation, which can be written as so this taking the derivative with respect to a vector, this is just like the gradient. This is equal to okay. If you're uncomfortable with doing this, let's just restrict to a one-dimensional case here. Okay, imagine that everything is in one dimension, and the I labels the particle number. Okay. Now, there's a dot. Okay, so if you just compute it, you'll find that what we end up with is this takes care of the 2, and then you have basically the time derivative of m times the velocity, which is ma. Right? So on this side you have ma. Now let me put the index I. And then on this side, well, for now, in the simple case, the kinetic energy is not dependent on the coordinates, only the velocity squared. Okay, so the time derivative, the coordinate derivative only acts on the potential function, and that is just analogous to the gradient, the ice gradient acting on the function. So this is just Newton's law. Okay. Now this is Lagrangian formulation. Okay, and I would like to remark that previously I mentioned something about painting a causal picture of classical mechanics, which is very simple in the Newtonian formulation, but in the Lagrangian formulation, what is the physical meaning of this action quantity? Why is it that the motion will actually minimize this action thing? Why is there a purpose to it? Well, we have shown to you that mathematically they're equivalent, but is there a way to think about it? A more intuitive way to think about it? Well, in classical mechanics, there are no way of doing this. Okay? But actually, as you learn quantum mechanics, towards the end of this course, you'll understand what is the real meaning of Lagrangian. Here's a very good answer offered by quantum mechanics. So that's what you will learn this semester. Okay. So now take a look at this equation. Okay. So we have written this as Newton's in the Newton's laws form. We can also write this as, of course, the time derivative of p. Okay. So we can associate this term with just the ith momentum in the system. Okay. And if we define it this way, it is possible to formulate classical mechanics based on momenta and coordinates. What we have done is formulate classical mechanics based on coordinate and velocities. So there's an alternative formulation based on the pi's and the qi's, and that is the Hamiltonian formulation.
You might want to mention that you derived the Lagrange equation or the Lagrange equation for one variable, and now you generalize it to multiple.
Okay. So to generalize it to multiple variables, just think about what we need to specify. Right? We need to specify there are 3 spatial coordinates typically, and for each particle we need to specify how it moves in the 3 spatial coordinates. So for each particle we're going to get 3 linear Lagrange equations corresponding. Yeah.
I just have a question like in the picture you drew. So we knew what T1 and T2 were, but how did you know what the Q1 and
those
T2
are
were?
because to solve the equation of motion, you must be supplied with initial conditions, right? Initial or boundary conditions.
I'm just kind of wondering, like, how would you know what the other position would have been at T2 anyway?
Okay, so there are 2 ways of doing it. It's a good question. We can have 2 ways of solving a second-order differential equation. We can specify 2 data here, or we can specify boundary conditions. But you need 2.
Oh, I know, but right, it's just because this is just a system acting on its own, and like otherwise, like, how do you know then what the other endpoint is?
For some
Because then at that point, if you don't know what the other endpoint is, then I'm not sure why you would bother with this, and it just.
It is also possible to formulate the Euler-Lagrange mechanics if I'm given the initial coordinate and velocity. It's also possible, but I'm not showing you that derivation here.
Okay.
I'm showing you that given boundary condition, if I know that this particle or the system evolves from this point to this point, and in some cases in some cases in mechanics that is a problem. But it's equivalent because to solve a second-order differential equation, you need 2 initial conditions. You need 2 constants. Okay. Does that answer the question?
Yeah, it was just more so like
okay.
this.
Yeah, I know. Typically, when we solve the differential equation, we think about giving the initial condition in terms of the initial coordinate and the initial velocity. But it's also okay to give the endpoints. Okay. So the Hamiltonian formulation then can be derived directly from the Lagrangian. Okay, for this, let us consider the total time derivative of a Lagrangian, and let's say for now that for simplicity, the Lagrangian is time independent. So the Lagrangian is only dependent on Q and the T. Well, let's just Q now. And there's no explicit time dependence. So let's construct the total derivative of this thing. And that will be given by, maybe we actually just T here. The total time derivative of the Lagrangian. Okay, and formally this is just going to be a sum over all of the dependent variables in there. Okay, so just the total derivative, not the time derivative. And so now, what we're going to do is, over here we have made this definition that the derivative, the partial derivative of the Lagrangian with respect to the ith velocity is going to give you the ith momentum. So let's replace this with the ith momentum over here. And let's use Euler Lagrange equation here. Replace this with the time derivative of the ith momentum. Okay. All right. And now let's operate on this term. Now we see that the infinitesimal quantity has a time derivative on it, and we would like to take the time derivative off of it. And to do that, what we can do is the total derivative of pi qi dot, and then minus, this is just doing chain rule, minus the other term. Okay, everybody understand this step? Okay. So now the other side is the total derivative of the Lagrangian. Okay. So now let's take this term to the other side. Okay. Which will give us Lagrangian minus this sum. Okay. Is equal to now we're going to apply a minus sign, and the reason for that is, notice that this, okay, if you think about a simple case, this is sort of like 1/2 mv coming from the p, okay, and then v, so mv squared. This is the, oh sorry, there's no 1/2 here. This is twice the kinetic energy, okay. And now we're taking the kinetic energy minus the potential energy, and then subtracting the kinetic energy, to twice the kinetic energy. If I put a minus sign on here, what I would expect is to get the kinetic plus the potential energy, which is the total energy of the system. So we want this quantity, so let's apply a minus sign to both sides of the equation. Okay, and that defines we're going to define a new quantity, which is this. And I just alluded to you that this is equal to the total energy of the system. And we call that the Hamiltonian of the system. And to go from the Hamiltonian, to go from the Lagrangian to the Hamiltonian, you apply this transform. Okay? And this equation says that the total derivative of the Hamiltonian is equal to its components, the derivatives in its component. So from here we can read off the equation governing the time variation in the momenta and the coordinate. Reading off from this equation, it says that so this is the equation of motion derived from here in the Lagrangian in the Hamiltonian formulation. And now what is good about these equations of motion is that we have achieved order reduction because both of them are first order in time. But to do the order reduction, of course, we have doubled the number of unknowns. So this is the Hamiltonian formulation. And the Lagrangian and Hamiltonian formulations, they are very good, and you should know at least a little bit about them, because if we do problem in the Newtonian way, then there's a need to specify the force acting on each particle. So the Newtonian problem is going to scale terribly as you go to complex systems. As the particle number increases, the number of forces is going to increase it's going to scale very badly because each particle is going to interact with another particle. But in the Lagrangian Hamiltonian formulation, these two scalars that correspond to the kinetic and potential energies, often it is quite simple to make an educated guess as to their form. So it's quite easy to write down T and V. And so once you've written down T and V, once you know the Hamiltonian or the Lagrangian, then deriving the equation moment is almost a mechanical exercise. So the problem remains in the Lagrangian and Hamiltonian formulation, remains doable for quite large systems. Okay. And now the last point we would like to illustrate with you, to you, and this is in connection with the importance of Hamiltonian in quantum mechanics, is that Hamiltonian as a quantity that governs the time evolution of any dynamical function. So for this, let's consider a general dynamical function that is dependent on the coordinate and the momenta of the system. Okay, so I can construct a dynamical function that is dependent on the momenta and the coordinates, and maybe there is also explicit time dependence. Okay, and now let's consider how this evolves in time. So we construct this total time derivative. And that is given by, first of all, you take care of the explicit time dependence, and then you're going to do this bracket thing. Now notice that the time derivative of the momenta and coordinate have appeared. So let's plug in the canonical. These are called the canonical equations because